right, well, the pandemic has taught us a few things. They've taught us that sometimes it's okay not to be in the room, even when you're presenting. So with that said, we really encourage presenters to be here in person. I want to thank everyone who has presented so far, because it just encourages that conversation, better dialogue, better back and forth. Go catch them at a break and ask a follow-up question type of thing. That's really important. So as we move into our next speaker, we have Suzanne Rhoades and Kevin Fitzgerald from Applied River Sciences are going to talk about fish in warm water. And so I'm going to stop sharing my screen. Suzanne, it looks like you're here and ready to go. Thanks for joining us remotely.
Yeah, thank you for having us, and thanks for bearing with us as Kevin and I are Zoom heads here. So we're going to be part B to the Shasta River Canyon study, and thanks to Eli Asarian for kicking us off here. So Kevin and I are going to talk about juvenile salmon growth modeling and pool stratification studies in the Lower Shasta River. And this work was done in collaboration with Riverbend Sciences, Eli Asarian, you just heard his piece of it, as well as Trout Unlimited, and River Science and Restoration, which is Todd Buxton, who helped us with the pool stratification piece. Okay, next slide, Kevin. So to give you a little bit of background on why we did this report, as many of you know already, the State Water Board is undertaking a permanent flow setting process for the Scott and Shasta River watersheds. So in 2025 and 2026, we undertook the Shasta River Canyon in-stream flow assessment. This was conducted to inform this flow setting process. The spatial scope of the study was just the Lower Shasta River at that point in time. That was the major point of compliance for the State Water Board at the Shasta River near Yreka gauge. Although, as Eli described, we did some upstream work thinking about the potential water temperature impacts upstream for any flows that are in the canyon. The goal of this study was to provide technical information that can inform the flow setting process, but also to provide a set of flow recommendations that can improve native salmon and productivity to increase population numbers and achieve resilience. And I want to mention that this report is really aiming at that question about what do fish need here, and it's not getting into at all like how we might actually get there for the watershed. So quantifying flows to support the fisheries is really just one piece of the puzzle for how we might improve flow management for salmon and population resilience in the Shasta River. There's some obvious next steps that this report does not do, like an implementation plan or examining the source of the flows and how they might intersect with water rights and infrastructure, and does not conduct any balancing of other water needs or uses in the watershed. Okay, next slide. So the aim of this report was to fill key uncertainties that in previous in-stream flow reports and documents on one of the most limiting seasons in the Shasta River, which is the spring and early fall. The irrigation season is in fact most impaired, particularly in the lower river when we're pretty far down from Juvenile. And we were focused on filling in three primary data and understanding gaps. One was flow and water temperature relationships, which we addressed with the empirical water temperature model with Eli Asarian from Riverbend Sciences, which you all just heard a little snippet of. There's much more in the appendix that he didn't even cover in his talk. The second question was, how suitable is seasonal rearing for the three salmonid species in the canyon, given that it tends to be a relatively warm place, even for the Shasta River. And then the third question was if there is any thermal refugia in the deep pools in the canyon. I'm going to talk really quickly here about this third set of thermal refugia in the deep pools because a little shorter story here, and over to Kevin, who's going to talk about the suitability of seasonal bioenergetics growth models. Next slide. You can go on. All right, so for the pool study, we sought to ask if the deep pools in the Shasta River Canyon are stratifying in this, providing any meaningful thermal refugia for juvenile salmonids. In addition, and what's their potential importance for juvenile salmonid over. We studied 2 pools in the Shasta River Canyon. We did not do inventory of pools, but we think Pioneer is if it's not the deepest pool in the canyon, then that pool has a max depth of 4 to 5 meters. We also instrumented Hudson Road Pool, which is further downstream in the canyon. The max depth was 2 to 3 meters, so a much shallower potential for pool stratification. Next slide. So each of these 2 pools was instrumented with set of arrays. They both have from the top of the pool down to the bottom of the oxygen loggers, stage recorders, lots of instruments going on in these pools. As kind of a quick preview for the results in the deeper pool, we saw that water were pretty warm, which is what we expected in the canyon, and that the temperatures at the bottom of the pool mimicked the temperatures at the surface of the pool throughout the day. So in the plot down here, you can see the lines are colored by depth, and the lines are pretty much all on top of each other. So there wasn't really, you might think, if pools are setting up to stratify, and this cold pool at the bottom of the pool is being maintained. So we didn't see that. There was some temperature variation between light, wasn't necessarily reaching all the way down to the bottom quite as powerfully as it is at the top of the pool, but this variation was typically less than 2 degrees Celsius for most days. There were just a few exceptions in there that we talk about in more detail in the report. And in contrast, just the daily variation in between temperature was more like 4 to 5 degrees Celsius. So the temperature swings that we're seeing across a single day was greater than we're seeing from the top to the bottom of the pool. This was the case in both of those pools, including the more deeper pool. Okay, next slide. And so as a summary of this study here, like I said, I would keep this one short and sweet. We did not see pool stratification set up in either of these pools. The vertical temperature variations were very low, less than 2 degrees Celsius for the far majority of the days throughout the summer. And we also didn't see the formation of thermoclines. So flow velocities remained too high in Pioneer Bridge Pool, where the water column was turbulent and mixing, so the top and the bottom was mixing throughout the course of the day. And in Hudson Road Pool, the shallow depths were too shallow and light was reaching the bottom of the pool throughout the daytime. We also looked for cold or warm water seeps and didn't see any of those pools. So that could have been another mechanism where if there's a cold water seep, that would be a source of cold water that could maintain cold temperatures at the bottom of the pool. We did not see that over the course of the summer. The report also described some numerical calculations for flows that would have to be, or how low flows might have to go to see stratification, and we did not see stratification at the lowest flow of 38 CFS that we observed over the course of the summer, which was conducted with a flow experiment in coordination with many people in the watershed. We did not see pool stratification set up at that low of a flow, and we think that flows would have to be much lower to really set up consistent stratification, at which point we'd be seeing a risk of extreme warming during these heat spells at a reach scale. So pool stratification might set up, but water temperatures overall would be warmer because there's less water mass in the water column. So it would be warmer temperatures at the top and warmer temperatures at the bottom, even if the layers are stratified. So in summary, we don't think these deep pools are really providing meaningful refugia for juvenile salmon in the canyon, and that likely wouldn't change at lower or higher flows that we were able to quantify. And there's a lot more information on this, more results and more calculations that are in the report. And this section was also led by Todd Buxton of River Science and Consulting. And so both here and I are available for questions if there are any more of these. And with that, I'll kick it off to Kevin to talk about the next part of the study.
Cool. Yeah, so I was sort of the lead on the bioenergetics juvenile salmonid growth simulations that we did to help determine um, what protective flows would be for juvenile salmon in the canyon reach of the Shasta. So I guess to start, I'll sort of like explain like why we chose a bioenergetic model, and then how we set that up, and then I'll sort of get into the results of this modeling exercise. So, um, if we think generally about like how we could select flows that are protective of juvenile salmon, there's many ways to do that, and I guess in like an ideal scenario, you would have empirical mechanistic flow fish productivity relationships that you could um, rely on to say like given X flow, we might predict X response in the population. However, um, those situations are really rare, and many systems are data limited, and the canyon reach of the Shasta is no exception to that. And so, more often, we rely on these flow habitat relationships, and kind of a classic example of that would be like the PHAB sim weighted usable area metric. That's very common in flow studies that our company and many others have done in the past. And in that, you essentially would take like a 2D hydraulic model domain of a reach and then divide it up into grid cells, and then input information about depth, velocity, and substrate, and it would output values of habitat quality, which then you could aggregate for given flow levels and look at these curves like we have here on the right part of this slide. So like if we look at that purple curve on the Hudson Road plot, for example, like you would identify, okay, like highest weighted usable area at 125. Um, However, like these approaches have some inherent flaws, particularly for this application where we're trying to identify flow thresholds in the canyon. Um, Probably the biggest one is that it's not inherently a temperature sensitive approach. It also does not directly incorporate food availability or growth condition. And then, if we think critically about it, if you had like a uniform channel with ideal values of depth and velocity, it would say that that is an optimal habitat, which we know that to not be true. So instead, um, we we look for maybe more informative, ecologically informative approaches, and so um, bioenergetics has a few different approaches that we can lean on for that. And so one of them that was fairly recently developed by Sean Naiman is this bioenergetics habitat suitability criteria, which is an individually based model which simulates the energetic quality of habitat in those grid cells in a 2D hydraulic model domain for fish. And so the inputs that you would put into that are depth, velocity, and then invertebrate drift, which you could collect at the site. And then outputs are net rate of energetic intake across flow conditions, which is just a metric describing the energetic quality for foraging of that habitat. Now, this is a more flow sensitive approach. It's a little more ecologically grounded, but it still has limitations. And again, it's not particularly sensitive to temperature, which is problematic for this application. The outputs of it are instantaneous, so it's just a single snapshot in time, which is problematic for evaluating the cumulative effects of flow and temperature conditions that we were interested in understanding over the duration of a whole irrigation season. And then it predicts the profitability of foraging, but not growth over that time window. And so we are very interested in understanding um, like the growth and the how high quality that rearing habitat could be or is currently. So another bioenergetics approach, which fixes some of these issues, but has some other limitations, is Wisconsin bioenergetics. And now that's an individually based model that simulates fish growth through time using an energy mass balance equation. And so, kind of simply put, there, it's like all the energy the fish would intake as food it's consuming is allocated towards these different costs. And then, since we're looking at juveniles, the only part of this in the green area that we're simulating is what's left over of that energy is available for somatic growth. In this model, the inputs you need are species parameters that have been pre-developed within Fish Bioenergetics 4.0, and then there's individual parameterizations for other species that exist out there. Consumption, like how much food it's eating, and then temperature, which influences the metabolic rate. And then the output is an individual fish growth curve. And as I said, limitations of this are that it's not inherently flow sensitive, and it's not explicitly incorporating habitat. It's just you're just saying how much it eats and what the temperature is. So we developed kind of a combined modeling approach here to reconcile some of these limitations of each of the of each of those modeling approaches. And so the data inputs that were required are like we need temperature, flow, the 2D hydraulic model domains, invertebrate drift, species energetic parameters, and then fish size and occupancy timing, so we can like initialize a body size and know how long to run a simulation for. And the two submodels within this modeling approach are that bioenergetics HSC one that I just talked about, and then also Eli Asarian's empirical water temperature model, which he just described in his previous talk. And then from those two submodels, we can get predicted temperature across flows and then predicted net rate of energetic intake across flows, which we'll use for consumption. And then we can tie in the species energetic parameters and then that empirical size and occupancy timing information from the CGFW rotary screw trap to create a simulation for an individual fish in a Wisconsin bioenergetics framework. And then all of that outputs an individual growth curve, which is incorporating information about flow, temperature, food, and habitat availability. So using that modeling framework, the objectives for this component of the flow study were sort of threefold. Our first objective was to understand growth conditions for juvenile salmonids in the Shasta River Canyon under the existing and unimpaired flows. Our second objective was to identify flows that maintain and enhance growth conditions. And then our third was to evaluate the flow recommendations that we developed through this method, and then a number of other informing data points. Evaluate those against the hypothetical unimpaired flows. So as far as field data that we needed to do this modeling, we needed to collect drift data. So we went out in the summer of 2025 at 3 different sites throughout the Shasta Canyon, as shown by these green points here. And we collected invertebrate drift samples 3 times. And then we had 2 2D hydraulic model domains that were from a previous study that our company had done in 2014. So once we got that invertebrate drift data, we're able to input that along with the 2D hydraulic model inputs into that bioenergetics HSC software to output values for consumption across flows. And so what you see in these plots here is like that total NREI value across flows for different size classes of fish. And we made an assumption here that those would be proportional to how much a fish is eating, and kind of the lingo the model uses like a proportion of the maximum consumption across stream flow, and so that's how we made the consumption element in the Wisconsin bioenergetics flow sensitive. And then the other flow sensitive input that we had were the temperature predictions across flows in the canyon from Eli's water temperature model. So we set up the simulations to simulate 3 species: juvenile chinook, juvenile coho, and juvenile mykiss. And then we did 2 age classes for those simulations: an age 0 and an age 1. And then we did separate simulations, kind of dependent on what the habitat of the canyon was primarily being used for juvenile salmonids. So our first was a simulation between April 1st and June 15th that was sort of like the out-migration window. And then the second was a summer rearing simulation beginning on June 16th and ending on September 30th. And then to the right, the spot here is some juvenile Chinook outmigrant data from the CDFW rotary screw trap. And so this is how we were parameterizing sizes, and we had them available for other species to start body size on those days and kind of ground these dates to be realistic. And then the parameterizations that we used for the species came from the fish bioenergetics software for coho and Chinook, and then we used a more regionally specific parameterization of mykiss from a paper by Yreka and Czech in 2000. So I will get into some results right now. So these are some of the output growth curves from that simulation. So we have individual years from 2009 to 2025 colored on these plots. And then that black line is like an average of those. And so this is specifically like the outmigration period here. That top row is mykiss, the middle is Chinook, and the bottom is coho. And what we can see from these plots from the outmigration period is that the existing flow conditions generally appeared to support positive growth for all species during the outmigration period, except for maybe towards the end for coho on the bottom there. They kind of started to level off, or in some years have experienced negative growth towards the end or point of that simulation. And then for the summer rearing period, we did the same thing, although from the June 15th to end of September time period. And from this, if we look to that top row there, we can see that mykiss, it generally appeared that mykiss may be able to successfully over summer rear currently in the canyon under existing conditions. But when we look to those Chinook and those coho growth curves below, it is not currently suitable for either of those species. We see those big depressions in the growth, which we just let it run. Like realistically, those fish would have either died or moved out of the system prior to experiencing that degree of negative growth. So that kind of gave us some understanding of how the habitat might be functioning under current conditions. But then we also did a threshold identification exercise where we looked at the distribution of body sizes when we held these flows constant across this range. And we were constricted by kind of the range of flows that Eli had. And so, yeah, I should probably move towards wrapping this up here. But yeah, during the spring outmigration period, we saw like peaks around 70 CFS for age zeros and 100 CFS for age ones. And then in the summer rearing period, we saw peaks around 50 to 70 for age zeros and 100 for the age ones, which was at like the maximum of what we were able to simulate. And sharp declines below 50 CFS, which would indicate that there's a very diminishing habitat quality below 50 CFS. And then these are the flow recommendations that were partially informed by the bioenergetic simulations and a bunch of other things. And I don't know that I'm going to get into, we get like a time check to see how much time I could kind of get into one other thing that we did here, or I could kind of end it on our flow recommendations. We're good on time? Cool. Yeah, so these are the flow recommendations that were developed. We have this water typing here of like dry, wet, and normal years, and we actually chose different recommendations depending on an adaptive water year typing approach. And so we chose to evaluate those flow recommendations using the bioenergetic models and compare against the observed flows, as well as 1 year of estimated unimpaired flow and temperature that was available from a Knoll et al. Study. And so for 2001. And so when we simulated the growth of mykiss, Chinook, and coho in that year across those three scenarios, we saw that the observed flows with our recommendations produce like the highest growth for mykiss and were somewhat improved relative to the observed flows for Chinook and Coho, although the unimpaired flows were substantially better for both of those. And interestingly here, like the Chinook salmon, the bioenergetic model suggested that the canyon would have historically been valuable over summer rearing for Chinook, but likely not Coho, although potential improvements on the shoulder seasons. And then we also kind of looked at it through the lens of like growth environment. So particularly for Coho, that might be more useful to understand like, okay, maybe they're not occupying the canyon for the entire summer, but like, did we improve conditions on the shoulder seasons or potentially improve conditions for fish that might be rearing in adjacent tributaries? And so here we see like, at the top, generally positive growth environment for mykiss. In the Chinook column, we see elimination of acutely lethal temperature days, going from the observed to the observed flows with our recommendations, and then almost total elimination of negative growth days when you look at the unimpaired year. And then on that bottom Coho row, we see elimination of the acutely lethal days with the observed flows implementing our recommendations. And then we see large decreases in the negative growth days going from that to the unimpaired. So some conclusions from all of this are that the canyon was likely historically an important summer rearing area for mykiss and Chinook and was more suitable for Coho on the shoulder seasons. Implementation of minimum flows would enhance and extend the period of growth for outmigrants and allow summer rearing of mykiss. And then I won't go too deep into this bioenergetics methodology conclusion component because it was I think I'm already over time here. But yeah, we have time. Happy to field any questions about that.
Yeah, thank you so much. We have time for a question or two. Anyone online? David.
Yeah, thank you. I've got a question about, I guess, limitations of the modeling. Am I correct that because you can't sample for drift under the variety of flow and temperature scenarios you're running, that you have to assume that drift or food availability is unchanged, even though flow and water temperature are being changed?
Yes, that would be accurate. So we're restricted to drift that we were able to observe under the conditions in the summer of 2025. And so those are the bioenergetics HSC software makes some assumptions generally about like how that would scale up to higher flows, but we did not have site specific like parameterization for drift at really high unimpaired flows during that time.
Thank you.
Yeah. Well, one thing that's interesting about the Shasta River, though, is it is very productive. So even in the impaired flow scenario that we're sampling in 2025, drift is really high when we compare how much drift and food there is to other sources and other places that have collected drift throughout North America. The Shasta River is on the upper end. So that's the good news in contributing to the fact that they can, particularly mykiss, can over-rear over summer throughout some of these warmer temperatures.
Well, Suzanne and Kevin, thank you so much for presenting and sharing all this interesting work.
Yeah, thanks.
Yeah.
Thank you.